That's so I don't forget to start the lecture, I think. It's going to count again. Mute. All right. How's that? Good. No echo? 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 This is really hard to do with a mask on. Okay. Feed speed, depth of cut, guessing, not recommended, carbide, explosion. You didn't know this was a class in poetry, did you? So what are the feed speed and depth of cut in CNC machining? We know something about this already. What is it? So what is the feed speed and depth of cut? I think we talked about this in 2 days ago. Tuesday, was that 2 days ago? We talked about this 2 days ago on Tuesday. Feed speed and depth of cut. I didn't call it out then, but I mentioned all of them. What's the speed that we care about in CNC machining? I mean, how fast we can do it, I suppose that's important to us, right? How quickly we can finish making the parts so that we can ship them to our customers, that's important. But when we talk about feed, speed, and depth of cut in CNC machining, we're not talking about that. What's the speed that we care about in CNC machining? But what's the one that we call speed? There's only one thing that we call speed in CNC machining. It's related to the spindle speed. So sometimes people will say speed and they'll call it RPM. And when they say RPM, they mean revolutions per minute, right? RPM is revolutions per minute. Don't forget that RPM is revolutions per minute. RPM itself is not a unit. It's a distance divided by time, right? It's the distance it goes in one revolution divided by time. So don't forget that. So sometimes we'll talk about speed as in RPM, and that's always the RPM of, this is where you guys say the spindle altogether, right? It's the speed of rotation of the spindle, right? So RPM is about the spindle. Now, often though, machinists, machine shop guys, programmers, and engineers that understand about this stuff, when they say speed, they know that it's related to RPM. That's not what they're talking about. When we do our cutting operations, oh look, somebody gave us a pretty design. And a happy Halloween. Wow. Sadness all around. They tricked my treat. Speed, RPM. When we do our cutting operations, we've got a cutting tool. I'll draw it better than that. We've got a cutting tool. It's got a sharp edge here. And so that's like looking at the edge of the sharp edge. So the sharp edge is coming out of the board at you. We're looking right down the sharpness. So this point right here denotes the sharpness of the edge of the cutting tool. And so if you've got that view in your mind, so in a milling operation, because you guys have seen the end mills now. In a milling operation, you get those flutes that spiral up the side of the tool. It's like you're lined up with the edge of the flute. Now, it's sort of hard. We'd have to like spiral the room around in order to spiral up the end mill and be staying on this point. But that point represents the cutting edge. So we're looking at a side view of the cutting. We've got some workpiece material. And so we've got to have relative motion between the cutting tool and the workpiece material, right? That's how cutting happens. And so we've got some workpiece material that's moving that way relative to the tool. And so there's like workpiece material. It hits the tool over here, and there becomes a new surface on the workpiece material. And then this stuff here slides up the edge of the tool and becomes the chip. So there's a chip that flows up the edge of the tool. Incidentally, you'll spend a whole week on this, but this edge that it's sliding up, that's called the rake face of the tool. And the chip slides along the rake face of the tool after it becomes not part of the workpiece anymore. So this speed that we're talking about is this velocity of the workpiece flowing past the cutting edge of the tool. That's the speed that we're talking about when we say feed speed and depth of cut. And so in a turning operation is a little bit simpler to visualize because it has fewer axes, fewer independent directions of motion, right? In a milling operation, you got X, Y, Z, and you got rotation of the spindle. In a turning operation, you've got rotation of the workpiece, and you've got X of the tool moving in and out on the diameter of the workpiece, and Z is the tool moving along the axis of the spindle. And so if we think about this, what's the speed then? We need to be able to convert RPM to this surface speed, which is this velocity of the workpiece flowing past the cutting edge of the tool. So you guys can derive this. I know you can. And then we're going to do this together. So what do we have? So I have another poem for you. Engineering's math, just a bunch of word problems, cancel the units. So the most important thing we do in engineering math is we make sure the units come out the way we want them to. And so when we talk about speed, the units, because we're dumb Americans, the units that we use are feet, because everybody likes to measure feet per minute. If we were in any other country in the world, we would be doing it in meters per minute. But since we're in America, it's feet per minute. Okay, so feet per minute. We know RPM. So we have RPM. We have revolutions per minute. We need feet per minute. How do we change from one to the other? If I know revolutions per minute and I want feet per minute, what do I need? There's going to be a pi in there. I mean, I like cake, but this time of year, pumpkin pie is nice. And pumpkin doesn't belong anywhere else on the menu. It doesn't belong in beer or coffee or scones. It belongs in pie. Rant finished. So there is a pi in the equation, I agree. But what do we need to know in order to go from RPM to FPM? Actually, we abbreviate this SFM just to make it more confusing. Yes. We need to know the radius or the diameter of rotation, right? And so in a turning operation, if we've got, let's see, got my piece here. So I got my workpiece here. I've got a tool here. The tool's feeding in this direction. The spindle's rotating in this direction. And so in this other diagram down here, we're looking down this edge. So it's like I was right here looking down that edge. That's this diagram over here. Okay, so we're feeding in this direction. We're rotating in this direction. We have an initial diameter. I don't know. Let's call it DO for D original. And we have a final diameter. I'm going to call that DF for D final. And so radius would be half the diameter, right? When I'm talking about speed, I always think in diameter instead of radius. And it's for a very specific reason that maybe I'll get into later. We'll talk about it in the labs. But I always think of this as diameter. And if I want to know what the radius of this part is, I even say half the diameter instead of radius. But so what's the relationship between diameter, RPM, and feet per minute? So how many, so if we look at the end view, right? If I look at the end view, and so honestly, there's a difference between this D0 and this DF, right? They're not the same, otherwise no cutting happened. It doesn't matter which one you use. Often I'll use the average, because so that's the surface speed at that point in the tool. If I want to know what's the worst case, what's the highest surface speed it could possibly be, I'll use the one out here because that's the biggest diameter we have. And if I want the smallest one it could be, I'll do this. Again, we're doing this because we're estimating. We're trying to understand what's happening at the cut. So we pick a diameter. Let's go with the D original because that's how big I drew the circle. So in each revolution, it travels this far, right? Each revolution, this much material goes past the tool edge. Every time it spins around once, this much material goes past the tool edge. How much is that? It's pi times diameter, right? So pi times diameter gives us inches per revolution. So if we multiply, inches per revolution. So this is pi times diameter. So if I take my RPM, multiply it by pi times diameter, the revolutions go away. I get inches per minute, which is almost feet per minute, right? It's pretty close. It's only off by a factor of 12. I don't remember stuff good. I don't know if you remember stuff good. Some people like to memorize formulas. Anybody ever write a bunch of formulas down on a note card? You remember, what was the class where you did trigonometry in high school? Did they call it trigonometry? We had a class like 9th grade, 10th grade, something like that, where you did all these triangle stuff, and there was like the circles with the triangles, all different directions in the circles. And you had to remember tangents and secants and cosecants and all that stuff. And you're supposed to remember all that stuff. I totally had it written on a sticky on the back of my calculator because they let us use calculators in the class. I don't know why they let us use calculators in the class. I cheated my way through trigonometry. Why should anybody memorize that stuff? You remember the ones that you use often. You don't remember the ones that you don't need. And as long as you know that it exists, you can go look it up. So maybe they'll take back my high school diploma. It's because now it's public record. I said it on the internet. And then maybe I won't get admitted to WPI. Oh, but maybe they'll give back all the tuition. Because I still have all the knowledge. Sweet. All right. Let's go for it, internet. All right, so we get it. I never remember if the 12 goes on the top or the bottom. And so I always do like, all right, inches per foot. That's not going to work. So I do feet per inches, and then I know that the 12 goes on the bottom. But every time I do it, if you're good at memorizing, go for it. Now, if you Google this equation, when I hit the button, it's going to start playing the video again. I know this from experience, and I know how to fix it, but I haven't fixed it on this presentation. Oh, this is a cool one. We'll come back to this one. Yeah, there's the picture I just drew. Look at that. Consistency. Oh, there's more of these. We'll come back to some of those. This is the one I was looking for. If you Google this, RPM to SFM, if you look up how to do this, you'll find a formula that looks like this. So you'll find a formula that says RPM equals SFM times 4 divided by tool diameter. Well, that's not what we just did here, is it? Or is it? What's 4 equal to? Yeah. 12 divided by pi equals 4. You know, if you're just estimating. 12 is 12, pi is 3, 12 divided by pi equals 4. That's where the 4 comes from in this equation. So if you're just estimating, sure, you could memorize this equation. But like I said, I'm not good at memorizing stuff. If you are, go for it. I think in all of the quizzes that I put on Canvas for this class, using this equation will get you an answer close enough to get the correct answer on the quiz. I'm not certain that that's true for the questions Professor Brown puts on the quizzes. Using this equation-ish mess that we have on the board, that will get you the correct answer every time. Often when we're doing this on the shop floor, we just need to be close. When the cutting tool manufacturers tell us what the recommended speed for the cutting tool is, and all the cutting tool manufacturers will tell you this. They'll tell you the recommended speed for the cutting tool. They tell you in units of feet per minute because the same tool might have different sizes. If it's like a spinny tool, so a milling tool, there's a bunch of different diameters, but they all have the same basic geometry, and they're all going to have the same recommended speed, but you have to multiply by the diameter to figure out how fast to spin the tool. And with a turning tool, it depends on this diameter, right? The surface speed that you end up with is going to depend on this diameter. Now, in turning, so this operation that we draw here, this is an OD turning operation. It's where we're reducing the diameter of the part. What if I wanted to make the part shorter? Could I just have the tool come across the front of the part? Notice I'm only going halfway because it spins around, it's rotating, so the other half gets taken care of. So I could just come across the face of the part like that. When we do that, we call it a facing operation, amazingly enough. So if we cut across the face of the tool, it's a facing operation. If we cut on the outside diameter of the part, it's a outside diameter cutting operation. What if I drill a hole in the end with a drill? Would you believe we call that a drilling operation? I could take a cool tool, a fancy tool, that's on a long stick that has a cutting edge that points out like that, and I could put it inside that hole that I drilled, and I could make the hole bigger. That's an ID, inside diameter, ID turning operation. All right, so we got OD turning, facing, ID turning, drilling. That's pretty much what happens in a lathe. You can do threading also. Threading is when you cut threads either on the outside or the inside. You need tools with special geometry, all that stuff. But the speed is in feet per minute. It's related to RPM by pi times the diameter, and if you want to have feet per minute and your diameter is in inches, then you're going to have to use a 12. And if they're metric units, there's like a 10 or 1,000 in there somewhere, right? If you have millimeters and you need to go to meters, that's a difference of, oh, come on, you guys know that one. If I have a millimeter, I want to know how many meters it is. What do I do? Divide by 12? Divide by 1,000. There's two reasons I ask these kind of math questions when I'm lecturing. One is because I don't want to misspeak and say the wrong thing. Because it's easy to like be in a hurry to get your point across and then not say the thing you meant to say. And two, no, actually that's the only one. It's just easy to screw up. So if I ask you guys and you say it wrong and I write it on the board anyway, I could pretend that I did it so that I was checking if anybody was going to correct it. Okay, that's the speed. So we talked about feed also, right? So speed, units are feet per minute. All right. We also talked about feed a little bit the other day, and I represented feed on the board here in one of those pictures also. The feed is the rate at which the tool is moving around in the workpiece material. So the speed is the cutting edge of the tool cutting through the workpiece material. The feed is the repositioning of that cutting edge so that there's material to cut. Does that make sense? So if I've got my turning operation, it's a lot easier to draw the turning operation. So if I've got my turning operation and I've got my cutting tool here, if it's spinning around like this, if it's spinning around like that, we know what the surface speed is, right? As long as we know the RPM. So we get this RPM this. We know what that surface speed is as long as we know what the RPM. And it's different here from here, right? This surface speed is smaller than this surface speed. So along that cutting edge of the tool, the surface speed is changing. But it's in that range. By the way, what's the surface speed right here in the center? 0. The surface speed at the center is 0, always 0. What about in a milling tool that's spinning around? What's the surface speed at the center of the milling tool? If the piece is not moving, it's 0. It could have some, so if there's a feed motion going on, it will be equal to the feed, right? Usually, surface speed numbers are in the range of thousands of feet per minute, and feed rate numbers are in the range of tens of inches per minute. So we usually ignore any feed component in surface speed. It's just usually not significant, except at the center of the tool, right? Because that's all the motion you have. So if you think about that, an end mill that's plunging down into the material, if it's going straight down into the material, there's no cutting happening at the center of the tool. There's the force from the motor that's turning the ball screw, that's pushing the axis down, that's mushing the center of the tool through the workpiece. But it's not cutting anything. It's just mushing it out of the way. And then the cutting, so for that reason, we don't like to plunge straight down into the workpiece with an end mill, ever. If you're moving sideways as you come down, then you will have removed the material before the center gets there. If you're spiraling down, you'll remove the material. Drills are specially designed, intended to go down. So if you have a drill, it's okay to drill down. In fact, don't go sideways with a drill. Only go sideways with end mills. And if you can, only go down with drills. There are certain end mills that are designed to cut downward, or so the designers say. Just avoid going straight down with an end mill whenever you can. All right, but anyway, off topic. So we know what the surface speed is. Will cutting happen? No cutting will happen the way I've drawn this so far. Cutting has happened over here, apparently, right? But unless we're moving the tool in this direction, we're not continuing to cut. So feeding the tool tells us how much we're cutting. The spinning of the workpiece causes the workpiece to go past that cutting edge of the tool, and that causes the cutting to happen. But we have to also feed And so what unit should we use for feed? If we're using our inch, pounds, foot unit system, what units should we use for feed? Yep.
Inches per minute.
We often like to look at inches per minute. And we usually write usually, it's really a matter of taste. Most people that I know usually write their G-code programs or their CAM programs to output G-code that gives you inches per minute, because it's the operator standing at the machine looking at the G-code has some intuition what inches per minute means, right? And so let's see. How far is this? This is about 60 inches, right? That's about 5 feet. And so if it took me 4 seconds to go 60 inches, how many inches a minute was it? You could calculate it though, right? But it's not very many. And I could try to go like, 60 inches a minute? No. 60 inches a minute is pretty fast though, huh? 800 inches a minute is pretty fast. Yeah, I'm pretty sure the VM2 that we use for the second operation of the Y block, that's capable of 800 inches a minute feeding. And then it doesn't have any more. The super mini mill might go a little bit faster, has less distance to go though. So we intuitively think in inches per minute. We can see it, but it doesn't tell us much about the life of the tool, right? Because how many inches it has gone in inches per minute, I don't know. What we usually do, and what the tooling manufacturers will usually tell us, is inches per revolution. How far does it go for each revolution? How far it has gone in a revolution. So if the next revolution brings it over here. So we could talk about feed in inches per minute, or we could talk about feed in inches per revolution. So this distance, if we've gone 1 revolution and it's gone that far, that's going to be related to how much material got removed to that revolution, right? So the cutting happens right here at the edge, or right here at the edge after 1 more revolution. The distance that we've gone, this area rotated around the part, is going to determine how much material got removed in that revolution. And so we like to talk about feed in distance per revolution. And we use inches. Sometimes we'll say inches per minute. When we use inches per minute, it's really for the convenience of the operator, because numbers for inches per revolution will be like 0.005, 0.010. Those are the kind of numbers you'll see for feed rates in a turning operation. And then depending on what the RPM is, that'll determine how fast it moves in inches per minute. Okay. What's the depth of cut then? Feed speed, depth of cut. Yeah. It's this distance here. And so it's the feed combined with the depth of cut that's going to tell you how much area you're removing as it goes around, right? And the depth of cut for a turning operation, if this is the original diameter and this is the final diameter, is going to be DO minus DF over 2, right? Because the depth is only measured on half but the diameter change happens all the way around. So our depth of cut. So feed speed, depth of cut. This will determine the volumetric material removal rate. The feed and the depth of cut actually will determine your volumetric material removal rate, which will determine how much power it takes. Well, that combined with material properties and some other stuff will determine how much power it takes to make the cut. And you have a question?
What if the depth of cut is
Then it won't be a constant. You can totally change depth of cut, right? And it does change as you're coming in and as you're coming out of the part and stuff like that. It does change. When we're modeling the situation, we tend to only model the parts that are steady state because it makes the math easier. But you could model each instance of band of steady state along that change, and you could figure out what's going on. And people do that with in the science and the research area here. At the shop floor, we try to limit the amount of time it spends changing and have it be constant as much as possible. It makes it more predictable. But yeah, that's a good point. Feed speed, depth of cut. All right, let's think about milling for a minute. So that's turning. If we're milling and we have a prism, I think I have a really good slide that shows this. See, I do know how to make slides. I just don't like to use them. There we go. This one shows it. And so if you look right here, can I zoom this, do you think? Maybe you know how to zoom this thing once it's in presentation mode?
You can do the Google page.
I can turn on the laser pointer. Is that going to work in the presentation mode? Control. It does make the thing bigger. Makes the laser pointer bigger. All right, laser pointer. All right, so we look at this part right here. And I just had the link to the presentation mode. I don't know what that is. If you look over here, so there's a depth of cut where the tool is coming down from the top of the workpiece, right? And there's a depth of cut where the tool is over sideways into the workpiece. Let me see if I can draw a picture. Might be a little bit easier to see. So if our cutting tool is here, so we've got our cutting tool here, and we've got workpiece here. There's a depth here, and there's this depth here. So in Esprit, the CAM software that we're using in the class, they call this the total depth, or they call actually the incremental depth. And they call this step over. In textbooks, we'll often call this, I think there's a video that shows it here too somewhere. No video. We'll save that one for a minute. So incremental depth, step over. One of them's axial depth. The other one is radial depth. Step over must be radial depth because it's how much depth along the radius you're going. And this is axial depth then. And so what's the step over times the incremental depth? Or what's the radial depth times the axial depth? It's an area, right? And it is an area that it's an area of material that's being removed for each feed increment, right? So if we're feeding in this direction into the board, it's going to remove this area for every feed increment. And so again, with the milling tools, our feed could be inches per minute, or it could be inches per tooth. So because the milling cutters have more than one cutting edge often, instead of inches per revolution, they do inches per tooth or inches per flute. And so to get inches per revolution is multiplied by the number of cutting edges on the tool. Feed speed, depth of cut. How do you avoid guessing when you're trying to figure out what these things should be? I suppose you could do the exercise in chapter 2 in the getting started with machining cam thing. So you look it up. You can, of course, you can buy a bunch of tools, and you could set up a test, and you could do a tool test, and you could figure out what speeds make the best cutting. But the tooling manufacturers, the people that make the tools, have already done that. So you guys don't have to, okay? So you can look it up. You look it up the tooling manufacturer's website. Sometimes you can just type in, so there'll be a part number on the side of the tool or on the box the tool came in. Type that into Google, say feed or speed, and it will bring you to a chart that tells you the feed speed and the recommended feeds, speeds, and depths of cut for that tool, for that material. All right, feed speed, depth of cut. What else did I want to talk about today? Oh, and choosing this wrong will cause the tool to explode. And too slow isn't better. So it's got to be in the correct range. Going too slow or having a feed that's too small. Well, if the feed's too small, it physically cannot create a chip in the next revolution. So what it ends up doing is burnishing the part. It ends up just rubbing the part, which puts a lot of heat into both the part and the tool. And so then maybe another revolution comes and maybe it still hasn't got enough to make a chip. Well, eventually all the forces build up and the tool goes and it breaks. And slow, also going too slow often wears out the tool much faster because all that extra heat you put in the tool. Too fast. Spinning too fast, having a spindle speed that's too fast, gives you the same problem as having a feed that's too slow. You get a lot of heat in the cutting area, and you wear out the tools prematurely. Feeding too fast makes the chip bigger. When the chip gets bigger, it takes more power to do the cutting operation, to form the chip, which means the cutting forces go up, which means the tool breaks. Sticking it out too far. Having too much incremental depth. So you have a total depth that you need to cut that's defined by the size or the shape of the feature on the part, right? The designer, the person that designed the part, tells you how deep you have to cut when they design the part. You get to decide in how many steps you do that depth with picking your incremental depth. If your incremental depth is too big, it has the same problem as your feed being too big. You add more force and you break the tool. Except also, who's ever pushed on something? What happens when you push on something? It moves that way. What if one end of it is fixed and can't move? You feel it pushing back on you, right? Forces and equal and opposite reactions and all that stuff. But as I'm pushing on the wall here, it's deflecting. You can't see it because I'm not pushing, I haven't put all my weight into it. But it's deflecting, and my hand is deflecting. My arm is like there's stress and strain happening in my arm and all that stuff, right? Same thing when you get the cutting force pushing on the end mill, it's deflecting. And the workpiece is deflecting. And the fixture is deflecting. And the spindle is deflecting. You can't measure a lot of it, but the deflection of the tool and or the workpiece, you can totally measure. You can see the difference visually sometimes. But what's deflection depend on? Who's had stress and strain? Or you talking about deflection in the stress and strain class, right? Who's had the class? So what, do you remember the equation for deflection of a simply supported beam? So we've got, and so just think of this as the tool holder, this as our end mill, and this as the place where we're applying the cutting force at the bottom of the end mill where we're doing the cutting. So do you remember the equation?
Force over area, over the chamber.
Well, so the distance that it's going to deflect, and instead of the equation, let's just think of what it depends on. So it depends on, what do we have here? We have a length. And so how far it's going to deflect depends on the length and the force. It depends on how strong the part is too, right? And so there's a material. There's like the elastic modulus for the material. There's an I that has to do with the geometry here. That's the area moment of inertia. Does anybody remember if the I goes on the top or the bottom of the equation? I think it goes on the bottom too. And then because this is round, the radius matters too. And so there's an R down here. Is that all the factors? I think that's all the factors. I think this is where they go in the equation. There's an important thing to know though. The length is cubed. So the amount of deflection depends on the force and the elastic modulus and the radius and the I value and the length, but the length is cubed. So the longer you hang that out there, the more likely it is to deflect. And if you hang it out just the right amount, it'll deflect and it'll cut, it'll vibrate back, it'll swing back and forth at a very high frequency. You'll be able to hear the frequency. It'll be really. Have you heard, the sound of the fingernails on the chalkboard? This sounds just as bad. I'm not going to demonstrate. I'm sure you'll hear it as you walk around the lab. Sometime it happens. So the length is important. Whenever you're setting up tools, put them as close as you physically can in the holder. So don't let anything hang out that doesn't have to hang out. Don't put them in so close that the holder is going to run into the workpiece material to get to the bottom of the cut, though. All right. I think that's about it. We got, 5 more minutes or so? Some lessons. I think I can turn the volume back on. That was it? Oh, come on. Never mind. Anyway, you can look up videos about tools crashing, machines crashing, or you could go to lab. It's kind of fractal. Or you could go to lab and crash one of those plastic end mills into the part. Raise your hand if you broke a plastic end mill. What was your reason for breaking the plastic end mill? It ran. Did you stop and check the distance to go first?
Yeah.
Did you decide to press cycle start? Yeah. Should you have?
No.
Was it cheaper than a $50 end mill?
Yes.
Thank you. Who did one that wasn't running into the vise? I know that you did. What happened to yours? Focused on how far it had left to go, and that was safe. The problem was it was in the center of the part instead of next to the part where it was supposed to be. So we watched for both of those things and we checked distance to go. And I want to thank you guys for being good sports, because we invented that lab just for you guys, based on the dismal experience we had last term at the end of the term with people breaking stuff. That check distance to go step, I think we certainly invented the enthusiasm for it here. That 6 steps on that safety checklist that we have you guys go through, that didn't exist when I started here. We invented that by observing crashes that happened, trying to ask the questions like what happened, what caused the crash, and then seeing, is there any policy that we could enact that would keep that kind of a crash from happening again, but also knowing we couldn't have a 76-step checklist because nobody would use it, right? I think 6 is the limit. I wanted to keep it to 5. It took us about $90,000 worth of crashes before we had settled on those 6 steps. So it's tongue-in-cheek when I talk about it, but it really is important. Since we started using the checklist, we have not had a single expensive crash that could not be attributed to somebody skipping steps on the checklist. And check distance to go is the last chance you have to catch screwing up further upstream. And so that's why we added this lab in at the beginning. It's been a lot of fun for me watching the plastic end mills break. They don't have the same, we should get a speaker. So they don't have the same satisfying that the carbide end mills have. But, oh well. Oh, and please, if you've decided to stop it, or if you have crashed already, make sure that you hit the e-stop. Get some practice. And that way, next time when you need to do it in earnest, you will remember where it is. I once bruised this part of my palm because I hit the jog handle on the way to the e-stop. In a full force, I've got to stop the machine right now moment. So if you have some practice, you won't have the same kind of e-stop injuries that I've had. And I'll see you guys in lab. Have fun. And next week there's class again, I guess, and Professor Brown will be here, and there's a schedule.